So now that we've had an opportunity to explore the definitions of matrix addition and scalar multiples, as well as some examples, we need to now take a moment to look at the algebraic properties of these two matrix operations. Now, these algebraic properties of addition and scalar multiplication with matrices are going to be particularly useful with theory and application to come. So let's take a look. So here, we want to let matrix A, matrix B, and matrix C be n by n matrices. We also want to go ahead and let C and D be any scalar our little hearts desire. So the first property says that the sum of matrix A plus matrix B is equivalent to the sum of matrix B plus matrix A. So the order doesn't matter. As long as they have the same size, we can combine these two matrices and we'll get the same answer either direction. Property number 2 says that if we have matrix A plus the sum of matrix B plus matrix C, again, the order doesn't matter. So we could take the sum of matrix A plus matrix B and then add matrix C, and we'll still end up with the same result. Our third property says that matrix A plus the zero vector, or the zero matrix, is going to leave us with matrix A. Our fourth property, or fourth through sixth properties, are going to incorporate scalar multiples. So the fourth property says that if we have the scalar multiple C of the sum of matrix A plus matrix B, this is equivalent to the sum of the scalar multiples. So C times matrix A plus C times matrix B. Similarly, if we have the sum of two scalar multiples, say scalar C plus scalar D times matrix A, this is equivalent, again, to taking the sum of the individual scalar multiples. So you have the scalar multiple C times matrix A plus the scalar multiple D times matrix A. And last but not least, if we have the scalar multiple of a matrix A, the order of your scalar multiples does not matter. So we could rewrite this as scalar multiple D multiplied by the scalar multiple C times matrix A, and we'll still attain the same result. Or we can use my favorite method where we take the product of these scalar multiples first and then multiply that new scalar by matrix A. So again, these algebraic properties are going to be particularly useful in theory and applications that we'll see very soon. And we can pretty easily verify all of these, or all 6 of these algebraic properties, using our knowledge of vector arithmetic. So let's take a peek at verifying one of these properties, and you'll be able to use the same technique to verify the others. So here we go. Let's verify property number 4. So we're asked to show that the scalar multiple C times the sum of matrix A plus matrix B is equal to the sum of the individual scalar multiples. So here is our proof. And again, this proof technique is going to be the same technique needed to verify the other 5 properties. So to begin, let's let A and B be m by n matrices such that we'll define matrix A by the column vectors A sub 1, column vector A sub 2, all the way up. Well, actually, let's consider the jth column vector here, all the way up to the last column vector A sub n. And we'll define matrix B using the column vectors B sub 1, we have vector B sub 2, somewhere in here we have the jth column vector B sub j, all the way to that very last column vector B sub n. Now we also want to go ahead here and let C be any scalar our little hearts desire. Now, in order to show that this is going to hold true for all column vectors, we want to consider the arbitrary column vector j. So let's go ahead and think about what's going on with the jth column vector. So we want to consider the jth column vector of matrix A and matrix B. So if it holds true for the arbitrary column vector, it holds true for all column vectors. So here we go. Thinking about that jth column vector, we have the scalar C multiplied by the sum of the jth column vector of A plus the jth column vector of matrix B. So another way to think about this is scalar C multiplied by the column vector A. So we have the entry in the first row jth column. We have the entry in the second row jth column, all the way down to the entry in the mth row jth column, plus the jth column vector of B. So we have the entry in the first row jth column, the entry in the second row jth column, all the way down to that last entry, B sub mj. So that's the entry in the mth row jth column. Now, by the distributive property of vectors, we can take the scalar C and distribute it through to both vectors, which leaves us with, we have our scalar C multiplied by that column vector of A, that jth column vector. So you have the entry in the first row jth column all the way down to the entry in the mth row jth column, plus scalar C multiplied by vector B sub j. So again, the entry in the first row jth column all the way down to the last entry. So that's the entry in the mth row jth column. Now wait a second, this is equivalent to saying we have scalar C multiplied by the jth column vector of A plus scalar C multiplied by the jth column vector of matrix B. So what we have shown is that the scalar multiple C multiplied by the sum of the jth column vector of matrix A plus the jth column vector of matrix B is equal to the sum of the scalar multiple of the jth column vector of A plus the scalar multiple C multiplied by the jth column vector of matrix B. And this is for all real numbers J, such that J is greater than or equal to 1, less than or equal to n. Now, since J is arbitrary, or since the jth column vector is arbitrary, this holds true for all column vectors. Woohoo! That's exactly what we needed. So this holds true for all columns of matrix A and matrix B. And we're ready to make our final conclusion. We can say that, therefore, we verified the property. We've shown that the scalar multiple of the sum of matrix A plus matrix B is equal to the sum of the scalar multiples. Woohoo! And that completes our proof. So, again, this technique of using our knowledge of vector arithmetic and using an arbitrary column vector of the matrices is going to hold true for all of these properties. So I challenge you now to go ahead and use this technique to verify the others.